So today I'll be discussing electric potential. Before coming to the point of electric potential, I will shed some light on few topics that are related to electric potential. First comes conservative nature of force. There are two types of force fields. One is conservative force field and another is unconservative, or it's better to call it non-conservative force field. So these are the two types of force fields. Now the difference between them is very simple. In the case of conservative force field, the total work done in going from one point to another point and then returning back is zero, total work done. But in the case of non-conservative force field, the work done in going from A to B and then from B to A, work done will not be equal to zero. That is, in the case of conservative force field, the work done does not depend on the path taken by the particle from traveling from one point to another point. But in the case of non-conservative force field, the path becomes important. So if we can bring it down to mathematical terms, it can be said that in the case of conservative force field, the line integral of electric field is independent of the nature of the path between the 2 points. So I am bringing it down to the electrostatic concept. So as electrostatic field is a conservative force field, so in this case too, the pathway will be not important, and only the 2 points, that is the initial and the final point, is the main deciding factor for evaluating the total work done in doing the process. So we can write that, suppose we draw a Cartesian diagram where at the origin a charge of plus q is placed, and we want to find the work done in bringing a test charge or a unit positive charge from point A to point B within the electric field made by the charge that has been placed on the origin. So this point is A and this point is B. So they will have their own position vectors, that is, this will be RA and this will be RB. It's better to write it here, RA, RB. These will be their position vectors, and the pathway connecting these 2 points is immaterial. I can draw anything I want, because no matter what pathway I draw, the net work done will be actually the displacement pathway, that is the shortest distance connecting the 2 points. So I can draw any pathway I want. Suppose there is another point here which has arbitrary position vector of r vector. point is P, and I want to find out that on moving a charge from point P to point Q, what amount of work is done. So if I join this point and consider the distance between P and Q as dl vector, and then if I extend this point, the point P, if I extend it, now as it is r vector, the extended part will be dr vector. Let me remove the point P. I can write it here, and I can give this part a new name, that is dr vector. What is dr vector? A very small amount of displacement in the direction of r vector, and then I can connect this point. Now what is the angle between dl vector and dr vector? That is theta. Theta is the angle between dl vector and dr vector. Okay, so this is the basic part. Now I can write that the work done in bringing a charge, test charge from point P to point Q. I am trying to bring this test positive charge from point P to point Q within the electric field of the source charge, that is plus Q. All the movements that I am doing is within the field of the initially residing positive charge, this charge that is already existing. This charge is actually influencing the field, and that is why the movement of the charge requires some work to be done. So the work done in bringing a test charge is a charge, a unit positive charge, that is being moved from one place to another in order to find out the electric field differences and electric potential differences. So the work done in bringing a test charge from point P to point Q will be equal to the force multiplied by the displacement. Now what is the force here? The force is the charge, test charge, multiplied by the electric field due to the source charge. This is known as source charge, and the charge that is being moved from point P to point Q is the test charge that we are moving. So the force will be Q0 into E, and the displacement will be dl vector, that is from P to Q. So this will be displacement. Now the test charge, as we know, is a unit positive charge, so we can consider that as 1, and this as E into dl vector. So E dl vector. Mind you, this is not a cross product, this is just a multiplication sign. As we are getting work from this product, it is always going to be a dot product. A scalar value cannot come out of a vector product, it always has to be a scalar product. So it will be a integration of electric field over dl to find out the work. This is known as line integral. This thing is known as line integral. This is known as line integral because we are integrating electric field over a line, that is dl. It's called known as line integral of the electric field between two points. Now the dl part is a very small part. We need to find out the total work done in moving the test charge from A to B. So what we need to do is add up all the small dLs to find out the total work done, the total displacement from A to B. So the total work done will be equal to E dot dl vector, that is the line integral from A to B. Now we know that the expression of electric field for a source charge, that is Q, will be equal to 1 by 4 pi epsilon 0 into Q by R square. And as we are writing the vector form, we need to show that the electric field will be in the direction of R unit vector, and therefore the work done expression will be equal to, that is integral of A to B E vector dot dl vector equal to integration of A to B 1 by 4 pi epsilon into Q by R square R unit vector dot dl vector. Now if we consider this R unit vector dot dl vector what is the angle between them? Theta. Dr vector and dl vector, R unit vector's direction is the same as dr unit vector's direction. R unit vector direction is this, dr unit vector's direction is also this. So the angle between them is theta, and therefore the dot product between them will be equal to R unit vector. So R unit vector magnitude dot dl vector's magnitude into cos theta. Now R unit vector's magnitude means what? 1. Therefore the integration from A to B 1 by 4 pi epsilon 0 into Q R square dl, no more vector sign will be given because it is a magnitude only, dl cos theta. Now what is dl cos theta? dr, if we consider this triangle here, then we'll see that cos theta is equal to base by hypotenuse, that is dr vector by dl vector, and therefore dr vector is equal to dl vector cos theta. So we can replace at this point the dl cos theta with dr vector. So we can write A to B 1 by 4 pi epsilon naught Q by R square dr vector, or dr, as it is dl cos theta, so we can write only dr, no direction sign is required. So that will be equal to work done or the line integral. It's better to write this way, E dl dot product integral, that is equal to work done from A to B. So we can write that A to B integral E vector dot dl vector is equal to 1 by 4 pi epsilon naught into Q integral A to B dr R square. Now we need to know a little bit of integration here. So 1 by 4 pi epsilon naught into Q minus 1 by R, definite integral from RA, that is position vector of A, to position vector of B, is equal to 1 by 4 pi epsilon naught into Q minus 1 by RB minus 1 by RA. So the result will be 1 by 4 pi epsilon naught Q 1 by RA minus 1 by RB. This is the line integral of electric field from point A to point B. that is actually the work done in moving a test positive charge within the influence of electric field of source charge from point A to point B. So we can write here that the line integral of the electric field between 2 points is same for all the pathways, we can also say all the path or the pathways between the 2 points. No matter what pathway we choose, the line integral of the electric field will be the same, because when we are getting the expression of work done, we are only getting the position vectors, and position vectors do not depend on direction, they only depend on the initial and the final positions. Therefore, as the expression does not contain any direction rule or any direction notations, therefore we can easily conclude that it only depends on the initial and the final position and is independent of any pathways. Now we can focus more on the features of this line integral. If we go from, suppose this is a Cartesian coordinate, and we go from A to B through this path, and then again come back from B to A through this path. So the line integral from A to B will be, as we know from the expression above, 1 by 4 pi epsilon into Q 1 by RA minus 1 by RP. Again, the line integral, as we have also come back from B to A, we have gone from A to B and then again come back from B to A, so we can write another line integral that is from B to A is equal to, what will be the difference in this case? The lower limit is B and the higher limit is A, so the expression will slightly change, that is 1 by RB minus 1 by RA. So if we see the total line integral from, at first from A to B and then from B to A, is equal to 1 by 4 pi epsilon into Q 1 by RA minus 1 by RB plus 1 by 4 pi epsilon 0 into Q 1 by RB minus 1 by RA. Actually these two terms will cancel out. Sorry, I didn't write E dot dl here. E vector dot dl vector equal to, so these two terms will cancel out and therefore we will get 0. So the line integral from A to B and then from B to A, the total line integral over this closed pathway is actually is equal to 0, and this actually proves the conservative force fields theory. That is, within a closed loop, if a charge is moved from one point to another point and then back to the same point, as we know that in the case of conservative force field the total work done is 0, it is supporting that theory that the total line integral of electric field over a closed pathway is equal to 0. We can write a line here that the line integral of an electric field along a closed path in an electric field is always 0. No matter what is the route, if the pathway is closed, that is from A to B and then B to A, no matter what pathway we follow, the line integral of that electric field along that closed path is always going to be 0. Now we know that the work done is equal to the line integral of electric field. So we can also come to the conclusion that not only the line integral over a closed pathway is 0, but the work done in moving a charge from one point to another and then back from that point to the initial point will be always equal to 0. So we can also come to the conclusion that B to A dot T vector is equal to 0. Therefore we can also write a line here that the work done in an electric field along a closed pathway is equal to 0. So the next point comes is electrostatic potential or electrostatic potential difference and potential from line integral. What is the relation between potential and electric fields? So at first, if we write the definition of electrostatic potential difference between 2 points, electrostatic potential difference between 2 points. The definition is the electrostatic potential difference between 2 points B and A is in an electric field is defined as the amount of work done per unit positive test charge in moving it from point A to B against the electrostatic force due to the electric field. So the electrostatic potential difference between 2 points B and A in an electric field is defined as the amount of work done, means how much work I need to do for moving 1 unit positive test charge from point A to B against the electrostatic force. So we always need to do the work against the electrostatic field, means if we are moving a positive charge in the electrostatic field of a positive charge, we need to bring them closer towards each other because we need to do the work. In the case of negative source charge, we need to take the test positive charge away from the center, so we have to do the work. So always the work needs to be done by us in order to calculate the potential difference. So if we draw a Cartesian coordinate diagram and consider 2 points A and B, give them their position vector name, that is RA vector and RB vector. connect the pathway through any way we want, to connect the 2 points by any pathway we want, and give an arbitrary point P, which will be given the position vector of r vector, and then say that there is another point Q which has slightly moved by dl vector from point P. Now if a source charge of plus Q is placed at the origin, then what do we need to do with the test positive charge that we are going to place here? We always need to move it towards the center, because the source charge will always impose a force on the test positive charge towards the outer side because of repulsion. And what we need to do is give an opposite charge of the same value so as to keep that in equilibrium, so that the charge doesn't move. So the amount of force that is being imposed on the test charge is charge of the force on which it is being imposed multiplied with the electric field of the source charge. So what is that? This force will be equal to Q0E. So the exact opposite amount of charge we need to put on it. Suppose the test charge is being moved a little bit, so the work done TW is equal to F vector dot TL vector, let us suppose, and this is equal to work done, the small amount of work done that is being done on the test charge. Now what is force? The force that is being imposed by us on the charge in order to keep it in equilibrium. So what will be its direction? The opposite in which the opposite in which the source charge is imposing the force on it. So the source charge is putting a force on this direction, in this direction, so the positive sign is there in front of it. But as we are putting a negative force, so we have to put minus Q0E force. It will be in the direction opposite of the force that the source charge is putting. So minus Q0E dot TL vector. Okay. So TW from A to B is equal to minus Q0E dot TL vector is equal to minus Q0 integration of A to B E vector dot TL vector. So what is this? The work done in bringing a charge from A to B, so that is written as this WAB is equal to minus Q0 integral of A to B E vector dot DL vector. So we can write WAB by Q0 is equal to minus integration of A to B E vector dot DL vector. Now what is the definition of potential difference between 2 points A and B? The electrostatic potential difference between 2 points A and B in an electric field. The electrostatic potential difference between 2 points A and B in an electric field is equal to the, what is it equal to? The negative of the, okay, first let's define potential difference and then we'll come to this concept. Let's first define electrostatic potential difference, then it will be easier for us to understand. the electrostatic potential, I think I defined electrostatic, okay, so I defined electrostatic potential difference in the beginning only. I didn't write the equation coming from it. The electrostatic potential difference between 2 points B and A in an electric field is defined as the amount of work done per unit positive charge. Means if I write the potential difference as VB minus VA, that is the potential of point B minus the potential of point A, is equal to the work done per unit positive charge. That means the work done in bringing out this positive charge from A to B per unit positive charge, means divided by the charge. Which charge? The test charge, not the source charge. So this is our equation. So we can identify this part, WABQ0, something that we have already got in this equation, this one. So we can replace it by VB minus VA, that is equal to minus A to B E vector dot dl vector. So now I can define what is potential difference in terms of electric field, as we have got this expression. So now it's better to write that the electrostatic potential difference, this part, the electrostatic potential difference between 2 points A and B in an electric field is equal to, what is it equal to? The negative of the line integral of the electric field between B to A. So it is equal to the negative of the line integral of the electric field between the points A and B. So we can also write it this way, that the electrostatic potential at any point. Now what we have written is two relative points, that is A and B, but we can also consider one point as infinity, is at infinity, and another point is at a certain point. So if we replace A with infinity, then we can understand that the potential of the position B, so what is the potential at position B, is equal to minus E dl line integral from infinity to B. That is, the work done in bringing a unit positive charge from infinity to B is equal to the potential at that point. So we can change this definition this way, that VB minus VA, where VA has been transformed into V infinity, that is the potential at infinity, is equal to the work done in bringing the test charge from infinity to point B. So we write it as B infinity by charge. Okay, so we'll not keep this integration sign here, WB infinity Q, and that will be equal to the line integral. Now we'll give the integral sign with the negative sign, because we know that the potential difference is always equal to the negative of the line integral between the concerned points. So E vector dot dl vector starting from infinity to point B. Now as a standard, we know that the potential at any point can be considered 0 by convention, and in our convention system we have considered the potential at infinity is equal to 0. This is by convention. So VB, this is by convention because the influence of an electric field at a point infinite distance apart from the source charge is actually 0. We know that. So it is considered that the potential at a distance, infinite distance away from the charge, can be considered as 0. So VB minus 0 is equal to W E infinity by Q, that will be equal to infinity b e dot dl vector. So Vb is equal to W b to infinity by q. Okay, so this q0, this is test charge, so you have to always write q0 here. These are all test charge. Okay, is equal to integral of infinity to b e integral dot dl. Okay, so it can also be written this way, that the Vb is equal to infinity to b e dot dl vector. This is the main equation that we need to find out. What is the relation between the electric field or the line integral of an electric field with the potential at some point, that we need to find out. So in accordance with this equation, we can write a line here that electrostatic potential at a point in an electric field is equal to, the electrostatic potential at a point in an electric field is equal to the negative, this negative sign is very important, the negative of the line integral of electric field between what? Between infinity to b, between infinity to that point. As we are not mentioning b here, so we will say that the negative of the line integral of electric field between infinity to that point. So we will end this lecture here. We'll start from the expression for electrostatic potential difference in the next lecture.